Okay, so spherical coordinates here. We've got some point in standard XYZ here, and we want to rename them. Now, spherical coordinates might be a little rusty from last year, but we measured them in rho, which is the distance from the origin. Okay, so it's not just the distance in the XY plane like the R value for cylindrical coordinates. Okay, it's the actual distance in 3D. And then the phi distance is the direction from the positive z-axis downward. So it's an angle measurement there. And then the theta value is our standard theta value for polar and cylindrical coordinates. So that one's the same as we've had before. And so we're wanting to change those x, y, z into this rho phi theta. Okay. And, the conversions then, I don't want to go too detailed on here, but let me just jot them down what they would be. That the x-coordinate then is rho sine phi cosine theta, and y is rho sine phi sine theta, and then the z value is rho cosine phi. Again, I know you saw these in Calc 2, and you can look these up in your textbook. The other thing, of course, we get just by the Pythagorean theorem in 3 dimensions is rho squared is x squared plus y squared plus z squared. Okay, so those are conversions. Now, if we're going to talk about integrating across a 3-dimensional volume region, or as we were calling it, region in class, then we've got to talk about, well, what happens as we go from, say, something that looks like this to an additional delta rho further away, and an additional delta phi further that direction angle-wise, further from the z-axis, and then likewise further delta, so a delta theta, so that would create a direction here. So at any rate, we get this sort of 3-dimensional piece, a piece of our region. Okay, I'm just going to move this out of the way here. All right, so this should be a little bit more box-shaped than it's looking. Maybe more like that. Okay, just go with it. Okay. Now, when we're figuring out this little box here, so this is a delta V, certainly it's approximately a rectangular box. Okay, yeah, the sides are curved, but the height here is certainly a delta rho. And as we start measuring out this direction, of course, the angle measurement that we increased it by was this delta phi additional angle. But if you recall, that means definition of radian measure here. The arc length then is rho times delta phi to give that length there. So we get a rho delta phi, and then this direction this way. Okay, actually let me draw that. That's the additional piece down here. Okay, I'm not able to draw this very well. So that's the distance this direction that we're going. That's how long that piece of the box is, sort of up top there, the back side of the box. So certainly it's the angle measure, the delta theta, times the distance from the origin. But notice this is just purely the xy plane. It's not the entire rho distance. It's just purely this distance here. Okay, so that's our previous r value. Okay, so we really want an r delta theta. That's really how long this side length is that we need for the last piece of our box. But what about the r value? Where does that come in? Well, the r value, another way of measuring that distance, the r, is to measure it right above it here. So there's the r value. And what I've drawn in here then is a right triangle, and our angle theta, by the way, it's the angle right down here. Oops. And so you can see that the sine of phi times rho would be the r value. Let me jot that down. So the r value is the sine of phi times rho. So if that's the r value, then this third side of our box, the r delta theta, is going to be r sine of phi delta theta, which we can then tack on to our delta v piece here. Oh, let me just kind of move things over a little bit, give enough room. And so this additional piece is rho sine phi, that's pretty bad phi, delta theta. So we said that's our delta v, our little change in volume. So of course in the integral, that dv then becomes, notice we've got two rows, so it ends up being a rho squared sine phi, and then we have a d phi, a d theta, and a d rho, or any order that you need it for your integration. Okay, so based on that, that gives us our conversion here. For our integral across our region of some function x, y, z, right, dx, dy, dz, and then that becomes equivalently in spherical coordinates in the rho phi theta of rho squared sine phi, and then again any order of d rho, d phi, d theta.